The MD5 message digest algorithm is a widely used cryptographic hash function producing a 128-bit hash value, typically expressed in text format as a 32-digit hexadecimal number. MD5 has been utilized in a wide variety of cryptographic applications, and is also commonly used to verify data integrity. MD5 was designed by Ronald Rivest in 1991 to replace an earlier hash function, MD4. The source code in RFC 1321 contains a by attribution (RSA) license. In 1996, a flaw was found in the design of MD5. While it was not deemed a fatal weakness at the time, cryptographers began recommending the use of other algorithms, such as SHA-1, which has since been found to be vulnerable as well. In 2004, it was shown that MD5 is not collision-resistant. As such, MD5 is not suitable for applications like SSL certificates or digital signatures that rely on this property for digital security. Also in 2004, more serious flaws were discovered in MD5, making further use of the algorithm for security purposes questionable. Specifically, a group of researchers described how to create a pair of files that share the same MD5 checksum. Further advances were made in breaking MD5 in 2005, 2006, and 2007. In December 2008, a group of researchers used this technique to fake SSL certificate validity. As of 2010, the CMU Software Engineering Institute considers MD5 cryptographically broken and unsuitable for further use, and most U.S. government applications now require the SHA-2 family of hash functions. In 2012, the Flame malware exploited the weaknesses in MD5 to fake a Microsoft digital signature. History and cryptanalysis. MD5 is one in a series of message digest algorithms designed by Professor Ronald Rivest of MIT. When analytic work indicated that MD5's predecessor MD4 was likely to be insecure, Rivest designed MD5 in 1991 as a secure replacement. In 1993, Denboer and Bosliers gave an early, although limited, result of finding a pseudo-collision of the MD5 compression function, that is, two different initialization vectors which produce an identical digest. In 1996, Dobertin announced a collision of the compression function of MD5. While this was not an attack on the full MD5 hash function, it was close enough for cryptographers to recommend switching to a replacement, such as SHA-1 or RIP MD160. The size of the hash value is small enough to contemplate a birthday attack. MD5CRK was a distributed project started in March 2004 with the aim of demonstrating that MD5 is practically insecure by finding a collision using the birthday attack. MD5CRK ended shortly after the 17th of August 2004, when collisions for the full MD5 were announced by Xiaoyan Wang, Dengo Feng, Zhu Jialai, and Hongbo Yu. Their analytical attack was reported to take only 1 hour on an IBM P690 cluster. On 1 March 2005, Ian Lenstra, Xiaoyan Wang, and Bernard Awega demonstrated construction of two X509 certificates with different public keys and the same MD5 hash value, a demonstrably practical collision. The construction included private keys for both public keys. A few days later, Vlastimil Klima described an improved algorithm, able to construct MD5 collisions in a few hours on a single notebook computer. On 18 March 2006, Klima published an algorithm that could find a collision within 1 minute on a single notebook computer, using a method he calls tunneling. Various MD5-related RFC errata have been published. In 2009, the United States Cyber Command used an MD5 hash value of their mission statement as a part of their official emblem. On 24 December 2010, Tao Xie and Dengo Feng announced the first published single-block MD5 collision. For security reasons, Xie and Feng did not disclose the new attack method. They issued a challenge to the cryptographic community, offering a $10,000 reward to the first finder of a different 64-byte collision before the 1st of January 2013. Mark Stevens responded to the challenge and published colliding single-block messages as well as the construction algorithm and sources. In 2011, an informational RFC 6151 was approved to update the security considerations in MD5 and HMAC MD5 security. The security of the MD5 hash function is severely compromised. A collision attack exists that can find collisions within seconds on a computer with a 2.6 GHz Pentium 4 processor. Further, there is also a chosen prefix collision attack that can produce a collision for two inputs with specified prefixes within hours, using off-the-shelf computing hardware. The ability to find collisions has been greatly aided by the use of off-the-shelf GPUs. On an NVIDIA GeForce 8400GS graphics processor, 16 to 18 million hashes per second can be computed. An NVIDIA GeForce 8800 Ultra can calculate more than 200 million hashes per second. These hash and collision attacks have been demonstrated in the public in various situations, including colliding document files and digital certificates. As of 2015, however, MD5 was demonstrated to be still quite widely used, most notably by security research and antivirus companies. Collision vulnerabilities. In 1996, collisions were found in the compression function of MD5, and Hans Dobertin wrote in the RSA Laboratories technical newsletter, "The presented attack does not yet threaten practical applications of MD5. But it comes rather close. In the future, MD5 should no longer be implemented, where a collision-resistant hash function is required." In 2005, researchers were able to create pairs of PostScript documents and X509 certificates with the same hash. Later that year, MD5's designer Ron Rivas wrote, "MD5 and SHA-1 are both clearly broken." On the 30th of December 2008, a group of researchers announced at the 25th Chaos Communication Congress how they had used MD5 collisions to create an intermediate certificate, authority certificate, which appeared to be legitimate when checked via its MD5 hash. The researchers used a cluster of Sony PlayStation 3 units at the EPFL in Lausanne, Switzerland, to change a normal SSL certificate issued by RapidSol into a working CA certificate for that issuer, which could then be used to create other certificates that would appear to be legitimate and issued by RapidSol. VeriSign, the issuers of RapidSol certificates, said they stopped issuing new certificates using MD5 as their checksum algorithm for RapidSol once the vulnerability was announced. Although VeriSign declined to revoke existing certificates signed using MD5, their response was considered adequate by the authors of the exploit. Bruce Schneier wrote of the attack that, "We already knew that MD5 is a broken hash function, and that no one should be using MD5 anymore." The SSL researchers wrote, "Our desired impact is that certification authorities will stop using MD5 in issuing new certificates. We also hope that use of MD5 in other applications will be reconsidered as well." In 2012, according to Microsoft, the authors of the Flame malware used an MD5 collision to forge a Windows code signing certificate. MD5 uses the Merkle-Damgard construction, so if two prefixes with the same hash can be constructed, a common suffix can be added to both to make the collision more likely to be accepted as valid data by the application using it. Furthermore, current collision finding techniques allow to specify an arbitrary prefix. An attacker can create two colliding files that both begin with the same content, All the attacker needs to generate two colliding files is a template file with a 128-byte block of data, aligned on a 64-byte boundary that can be changed freely by the collision-finding algorithm. An example MD5 collision, with the two messages differing in 6 bits, is D131 DD02C5E6 EEC4693 D9A0698 AFF95C2 FCAB58712467 EAB4404583 EB8 FB7F8955 AD340609 F4B302 83 E488832571415 A085125 E8 F7CDC99 FD91 DBDF280373 C5B D8A23E315634 F5BA60 ACD436 C919 C6DD53 E2B487 DAR03 FD02396306 D248 CDA0E99 F33420 F577 E8 CE54B67080 A80D1 EC69821 BCB6 A88393 96 F9652 B6 FF72 A70 D131 DD02C5E6 EEC4693 D9A0698 AFF95C2 FCAB50712467 EAB4404583 EB8 FB7F8955 AD340609 F4B302 E48883225 F1415 A085125 E8 F7CDC99 FD91 DBD7280373 C5B D8A23E315634 F5BA60 ACD436 C919 C6DD53 E23487 DAR03 FD02396306 D248 CDA0E99 F33420 F577 E8 CE54B67080 D1 EC69821 BCB6 A88393 96 F965 AB6 FF72 A70 both produce the MD5 hash 79,054,025,255 FB1A26 E4BC422 AEF54 EB4. The difference between the two samples is the leading bit in each nibble has been flipped. For example, the 20th byte in the top sample, 0 by 87, is 10,111 in binary. The leading bit in the byte is flipped to make 0000111, which is 0x07 as shown in the lower sample. Later it was also found to be possible to construct collisions between two files with separately chosen prefixes. This technique was used in the creation of the Rogue CA certificate in 2008. A new variant of parallelized collision searching using MPI was proposed by Anton Kuznetsov in 2014, which allowed to find a collision in 11 hours on a computing cluster. Pre-image vulnerability. In April 2009, a pre-image attack against MD5 was published that breaks MD5's pre-image resistance. This attack is only theoretical, with a computational complexity of 2123.4 for full pre-image. Other vulnerabilities. A number of projects have published MD5 rainbow tables online, which can be used to reverse many MD5 hashes into strings that collide with the original input, usually for the purposes of password cracking. The use of MD5 in some websites' URLs means that search engines such as Google can also sometimes function as a limited tool for reverse lookup of MD5 hashes. Both these techniques are rendered ineffective by the use of a sufficiently long salt. Applications. MD5 digests have been widely used in the software world to provide some assurance that a transferred file has arrived intact. For example, file servers often provide a pre-computed MD5 checksum for the files, so that a user can compare the checksum of the downloaded file to it. Most Unix-based operating systems include MD5. Some utilities in the distribution packages. Windows users may install a Microsoft utility, or use third-party applications. Android ROMs also utilize this type of checksum. However, now that it is easy to generate MD5 collisions, it is possible for the person who created the file to create a second file with the same checksum. So this technique cannot protect against some forms of malicious tampering. Also, in some cases, the checksum cannot be trusted, in which case MD5 can only provide error-checking functionality. It will recognize a corrupt or incomplete download, which becomes more likely when downloading larger files. MD5 can be used to store a one-way hash of a password, often with key stretching. Along with other hash functions, it is also used in the field of electronic discovery, in order to provide a unique identifier for each document that is exchanged during the legal discovery process. This method can be used to replace the bait stamp numbering system that has been used for decades during the exchange of paper documents. Algorithm. MD5 processes a variable length message into a fixed length output of 128 bits. The input message is broken up into chunks of 512-bit blocks. The message is padded so that its length is divisible by 512. The padding works as follows. First, a single bit, 1, is appended to the end of the message. This is followed by as many zeros as are required to bring the length of the message up to 64 bits, fewer than a multiple of 512. The remaining bits are filled up with 64 bits representing the length of the original message, modulo 264. The main MD5 algorithm operates on a 128-bit state, divided into 4 32-bit words, denoted A, B, C, and D. These are initialized to certain fixed constants. The main algorithm then uses each 512-bit message block in turn to modify the state. The processing of a message block consists of 4 similar stages, termed rounds. Each round is composed of 16 similar operations based on a nonlinear function f, modular addition, and left rotation. Figure 1 illustrates one operation within a round. There are 4 possible functions f. A different one is used in each round. Denote the XOR, and, or are not operations respectively. Pseudocode. The MD5 hash is calculated according to this algorithm. All values are in little endian. Note: all variables are unsigned 32-bit and wrap modulo 2*32 when calculating var int 64 s. K per second specifies the per round shift amounts s 0, 15 equals 7, 12, 17, 22, 7, 12, 17, 22, 7, 12, 17, 22, 7, 12, 17, 22, s 16, 31 equals 5, 9, 14, 20, 5, 9, 14, 20, 5, 9, 14, 20, 5, 9, 14, 20, s 32, 47 equals 4, 11, 16, 23, 4, 11, 16, 23, 4, 11, 16, 23, 4, 11, 16, 15, 23, S, 48, 63, equals 6, 10, 15, 21, 6, 10, 15, 21, 6, 10, 15, 21, 6, 10, 15. 21. Use binary integer part of the signs of integers as constants. For I from 0 to 63 k, I equals floor, end for k, 0. 3 equals 0xd76 AA 478, 0x C8C7B 756, 0x 242,070 decibels, 0xC1BDCEE K 4, 7 equals 0xF57C0FAF 0x4787C62A 0xA8304613 0xFD 469,501 K 8 11 equals 0 by 698,098 D8 0 by 8 B44 F7AF 0xFFFF5 BB1 0x895 Candelas 7B K 12 15 equals 0 by 6 B901122 0xFD 987,193 0xA6794380 0 by 49 B40821 K 16 19 equals 0xF61 E2562 0xC040 B340 0 by 265 E5A51 0xE9 B6C7AA K 20 23 equals 0xD62 F105D 0x02441453 0xD8A1E681 0xE7D3FBC8 K 24 27 equals 0 by 21 E1CDE6 0xC33776 0xF4D50D87 0 by 455 A14 ed K 28 31 equals 0xA9E3E905 0xFCEFA3F8 0x676F02D9 0x8D2A4C8A K 32 35 equals 0xFFFA3942 0 by 8771 F681 0 by 6D9D6122 0xFDE5380C K 36 39 equals 0xA4BEEA44 0 by 4BDECFA9 0xF6BB4B60 0xBEBFBC70 K 40 43 equals 0 by 289 B7EC6 0xCAA127FA 0xD4F3085 0x04881D05 K 44 47 equals 0xD9D4D039 0xE6 decibels 99 E5 0 by 1 F827 CF8 0xC4 at 5665 K 48 51 equals 0xF4292244 0 by 432 AFF 97 0 Shab 9423 A7 0xFC 93 A039 K 52 55 equals 0 by 655 B59 C3 0 by 8 F0 CCC 92 0xFF 47D 0 by 85,845 DD1 K 56 59 equals 0 by 6 FA 87 E4 F 0 X FE2 CE 6 E0 0 X A 3,014,314 0 by 4 E0811 A1 K 60 63 equals 0 X F7537 E82 0xBD3AF 235 0 by 2 add 7D2BB 0xCB86D391 initialize variables var int A0 equals 0 by 67,452,301, a var int B0 equals 0 zfdb 89, b var int C0 equals 0 by 98 BADCFE, c var int D0 equals 0 by 10,325,476, d preprocessing. Adding a single 1-bit append 1 bit to message asterisk notice. The input bytes are considered as bit strings, where the first bit is the most significant bit of the byte. Preprocessing. Padding with zeros append 0 bit until message length in bits 448 append original length in bits mod to message. Process the message in successive 512-bit chunks. For each 512-bit chunk of message, break chunk into 1632-bit words M, J, 0, J15. Initialize hash value for this chunk. var int A equals A0 var int B equals B0 var int C equals C0 var int D equals D0. Main loop. For I from 0 to 63 if 0 I15 then F equals or and D, G equals I else if 16 I31 F equals or and C, G equals mod 16 else if 32 I47 F equals B XOR C XOR. DG equals mod 16 else if 48 I63 F equals C XOR, G equals mod 16 D temp equals DD equals CC equals BB equals B plus left rotate. SIA equals D temp N4. Add this chunk's hash to result so far. A0 equals A0 plus AB0 equals B0 plus BC0 equals C0 plus CD0 equals D0 plus D. End for var char digest. 16 equals A0 append B0 append C0 append D0. Left rotate function. Definition: left rotate return binary or note. Instead of the formulation from the original RFC 1321 shown, the following may be used for improved efficiency. F equals D XOR, F equals C XOR, MD5 hashes. The 128-bit MD5 hashes are typically represented as a sequence of 32 hexadecimal digits. The following demonstrates a 43-byte ASCII input and the corresponding MD5 hash. MD5 equals 9E107 D9 D372 BB 6826 BD81 D3542 A419 D6. Even a small change in the message will result in a mostly different hash, due to the avalanche effect. For example, adding a period to the end of the sentence. MD5 equals E4 D909 C290 D0 FB1 California 068 FFA DDF 22 CBD0. The hash of the zero-length string is MD5 equals D41 D8 Candelis 98 FOOB 204 E9800998 ECF8427E. The MD5 algorithm is specified for messages consisting of any number of bits. It is not limited to multiples of 8-bit as shown in the examples above.